The natural progression after talking about the area of a rectangle is to then lead into the area of a triangle. It's all something that you all have perhaps seen before, at least the formula, and I want to walk through that and some specific examples. So this video shouldn't be that long. The area of a triangle with base B and with corresponding altitude that has a length of h. Remember that the altitude is perpendicular to that side, that base, is given by the area is 1/2 the base times the altitude. For non-right triangles, this is fairly easy to apply, and for right triangles as well. There are two different cases for non-right triangles where I have some particular base and the altitude falls on the inside of the triangle. And I may need to use some method that I've established or the given information to figure out what the height is. The other case is where the altitude falls on the outside of the triangle. And I want to remind you that the altitude is defined in such a way that it is not required that it has to fall on the inside of the triangle, but rather it still should be the line that can, or it should still be perpendicular to the line that contains the opposite side. That this is the h and this is still the base side. Either way, the formula is still the same, that the area is still 1/2 times the base times its corresponding altitude. I can't just choose any altitude and any base. They have to correspond and be perpendicular to each other. So look at some examples. Find the area of triangle ABC, given that AB, that's this base here, has a length of 10, and CD, its corresponding altitude, has a length of 7. I mean, there's no trick here. The area is 1/2 base length 10 times the altitude length 7. So that's 70 divided by 2, or 35. That the area is 35. They get more complex than this. For instance, even just stepping it up one notch, given that the triangle ABC is a right triangle, AC is 17, BC is 8. Find the area of triangle ABC. Well, I can't do that just given this information because I'll remind you that I need to have a base and its corresponding altitude. And it turns out if I'm looking at a right triangle, a right triangle's legs are always perpendicular to each other. So in order to find the area here, I'm either going to do a lot of work by drawing in the altitude from B and figuring out all these proportions, or I could use the Pythagorean theorem to figure out this side x and use x and 8 as the perpendicular altitude and its corresponding base. Using the Pythagorean theorem, I can do that. X squared plus 8 squared is equal to 17 squared. X squared plus 64 is equal to, 17 squared I think is 289. Let me check that. 17 squared. Yeah, it's 289. Whew. I think I can remember some things sometimes. Subtract 64 from both sides, and x squared is equal to 289 minus 64 is 225, or that x is equal to the square root of 225, which is 15. So from there, I can calculate the area. The area then is 1/2 the base times its corresponding altitude, which in this case is 1/2 15 times 8, which is just 4 times 15, or 60. The area of this triangle is 60. Again, they get a little more complex, but I'm still going to walk you through some of the examples, and I'm going to ask that you stay in this because it does get a little more complex. If a triangle is obtuse and has an angle A, and triangle DEF is an acute triangle, how do these specific triangles compare in area? Well, this is trying to highlight the thing that I was telling you, that they both have bases of length 8, and both of their altitudes are a length of 6. Therefore, these two triangles are both going to have an area that is 1/2 times base times the altitude, which is 24. Both of them have an area of 24. Just because they look different doesn't mean that they can't have the same area. And I want to draw you back to one of the area postulates where we said that um, equivalence was the name that we called to this property, that if two figures have the same area, it's called equivalence, that these two are equivalent. One additional thing that we'll study in this area unit is this notion of composite figures, which are just figures that are made up of two different things that we've seen before. So this first one, the figure ABCEF, is just the sum of what the area of that rectangle below it is and the area of the triangle is. So if I can find them separately and add them together, I have the area of the entire thing. Using that, let's find the area of WXYZ, remembering that we do need units in this piece. Well, the area of WXYZ would be separate it into pieces that we can easily see and work with. Maybe I'll separate it into this triangle here, the red triangle, and then this blue triangle here. Find those areas separately and add them together because the area addition postulate would allow us to do that. So first, note that the area of WXYZ is the area of that blue triangle, WXZ, plus the area of the red triangle, XZY. And then from there, proceed to find the areas of those figures. This is going to be problematic right off the back, though, because I need a base and its corresponding altitude. And the thing that's missing for both of them is this green side here. So pick one of the triangles, solve using the Pythagorean theorem for xz, and then I can solve for the area for both of them. 5 squared plus, I'll call that x. X squared is equal to 13 squared. 25 plus x squared is equal to 169, or that x squared is equal to 144. Therefore, x better be 12, that this side is 12. So the area of WXZ, the blue triangle, is 1/2 base, which is 12, times its altitude, which is 5, plus the area of XZY, which is the red triangle, 1/2 base, which is 12, times its altitude, 16. And doing that, by solving out, I'll get the area of WXYZ. So let's just do that. Let's see, 1/2 times 12 times 5, that's 60 times 1/2 is 30, plus 12 times 16 is 192, times 1/2 is 96. So the area of WXYZ is 30 plus 96, or 126, and then just remembering those units there, inches squared. The last little piece I want to throw at you is that we can do this for few other instances. Like, for instance, if I have a shape that I know that I can break into triangles, things that I've seen before, like a parallelogram, maybe I can find its area without needing to first find its own area formula. That's typically how it's done. So consider I have a parallelogram and I draw in the parallelogram's altitude. An altitude of a quadrilateral, I'll remind you, is a segment that goes from one vertex and is perpendicular to the opposite side. This is, I've drawn in here, is an altitude. What type of triangle is this red one that I'm outlining? It's a 45, 45, 90 triangle. Knowing that it's a 45, 45, 90 triangle, I'm going to draw it separately out here so we can figure out those lengths. It's a 45, 45, 90 triangle with a hypotenuse of length 15. Remember the special right triangle relationships that we established that said if I had a 45, 45, 90 triangle with a leg of length x, the other leg has a length x, and the hypotenuse has a length of x root 2. That will help us figure out what this x piece is. Um, so let's see, 15 is equal to x times the square root of 2, or that x is 15 divided by the square root of 2. Rationalizing by multiplying by the square root of 2 over the square root of 2, the altitude is 15 square root of 2 over 2. Now, if I wanted to get complicated, I could also do that over here, noting that that triangle would end up being congruent to this red outlined one. The blue one would be congruent to the red outlined one. And then in the middle, I would have I should use green, rectangle that I could just find each of those areas, the things that I know, and add them up to get the area of the entire thing. We'll see a method to work with that, but that might not be the most efficient way. The last thing that I want to throw at you is we do study trigonometry because it allows us to find area in one additional way. That the area of a triangle is given by 1/2 times the product of two sides times the sine of the angle between them. It has to be the sine of the angle between those two sides. Just keep that in mind. So I'll do this one example with you and I'll be done. The area of triangle ABC in this case, I could go through and use the law of sines, law of cosines to figure out all the other sides and the altitude. That's a lot of work. Or I could use the trig formula, that the area of triangle ABC is 1/2 times two consecutive sides. Well, turns out 17 centimeters and 11 centimeters are two consecutive sides. And then the sine of the angle between them. And that'll give us the area. 1/2 17 times 11 times sine of 16, well, or 60, I'm sorry. Why don't we just pull out the calculator for that? Times 11 times the sine of 60. And I get that that's approximately equal to 17 times 11 times sine 60 would give me approximately 80.97 centimeters squared. That's how you find the area of a triangle. It's fairly straightforward. If you have any questions, feel free to ask me.